Good afternoon. Okay. Yeah, my name is Huidae. I'm going to talk about this continental scale hydrologic modeling using grass. And yeah, I go by Huidae, this name, and I got my degree in water resources engineering, grass development since 2000, and 10 years industry experience. I got one user of my module, right? Our water outlet less M, right? And so let's talk about hydraulic modeling. So this is very basic workflow, very linearized, very simplified workflow, and mostly just about hydraulic parameters only. And we do modeling after this step. So basic step is you start from DEM, right? Digital elevation model, and you sink fill, you remove all these dams because otherwise you cannot really let water flow through these dams or reservoirs or the thing. And then you have hydro enforcing, meaning you kind of sync your DEM data with actual natural hydrology by burning your data, and you calculate flow direction and accumulate your flow, number of cells, and some weighting, and delineating watershed boundary, and get a stream network, and you find the longest flow path for, let's say, for time of concentration within your watershed, how long it takes to drain all this water, right? For that, you need that physical parameter called longest flow path. So my motivation for this talk is basically we have almost 92,000 dams in the US, and I wanted to calculate most of these parameters for these dams. And it's too many. And the DEM is 30-meter DEM from USGS. That's about, if I remember correctly, that's about 50 billion cells in the US. That's a lot. And now existing solutions are that accumulate. It's a sequential algorithm, but it can do many different things. And then we have a fast flow, some open source, outside grass, and ArcHydro commercial. You have some limited parallelization. And then tau DM, and it's MPI parallelized. MPI parallelization versus OpenMP means OpenMP is a single computer parallelization. MPI is multiple computer parallelization. But its use of MPI is limited to a single node. So meaning it uses only multiple cores in one CPU. There's some limitation. And rich DEM is, it's really great because it has hybrid parallelization, OpenMP plus MPI, but it's missing some important, module for watershed delineation. Right? So what do we do? Oh, this one, another one is a high performance flow accumulation. It's a OpenMP, but they don't really cover all my use cases because I need most of these parameters and some nice parallelization. So challenges, 15. So challenges, so 30-meter DEM for the Konos has 15 billion cells, and input flow direction we usually use 1 byte per cell, meaning input flow direction alone takes up 14 gigabytes of memory. And most of those previous existing solutions use intermediate matrices or intermediate outputs, and they take up space, almost same space, like 14 gigabytes. And output flow accumulation takes up 56 gigabytes. And this plus this, well, more than 64 gigabytes. And my system has only 64 gigabytes. We do, right? That's one problem. And then output watershed, 56. So blah, blah. So minimum memory, 84. My maximum memory, 64. And my brain has even shorter memory. Yeah. So what do we do? And the problem with this intermediate matrix, you spend a lot of time and computing resources to compute these intermediate things. that you will never see after your algorithm. It's waste of memory and waste of I/O, waste of computation resources. So I started with my sequential algorithm called R.accumulates. That was sequential, but it's still better than other sequential algorithms, but it's limited, obviously. But here, star means it can do many different things. That's what it means. And then after that, I was interested in parallelization, OpenMP parallelization. So I developed this R.flow accumulation. It is OpenMP parallelization. And in this algorithm, I just got rid of that medium, intermediate matrix, whatever, no more. So what does it mean? You can reduce number of writes, number of bytes, right? To and from that intermediate matrix. And this saves a lot of memory I/O, saving computational time. And my next challenge was watershed delineation. Now it's called R.hydrobasin. Initially it was R.watersheds, like on the S difference. So I renamed it R.hydrobasin. And then, and I have this now. I have to revise it by Monday. So hopefully I can do that. So this is a parallelized version. I do have sequential version with same name. I'm going to overwrite that. So we have these three parallel algorithms now. And this is how it works. I have this kind of time, but it's memory efficient flow accumulation, MEFA. And it reduces number of writes and bytes, and benchmark algorithms compared to benchmark algorithms, very highly reduced number of highly reduced memory usage thing by using some look ahead and behind kind of technique. So here you can tell. So this is total number of byte operations. You see big difference here. And then this is a benchmarking. So this is mine, others, and ArcGIS. Yeah, no SLE, right? And our hydrobasin, so for that 64 megabyte, gigabyte thing, so I use input destructive, meaning I just have input and output matrix, and no, not even input and output. I just have one matrix, input and output union matrix. I started with input data only, and then I overwrite that input as I compute output, right? So it reduces this memory usage. And this is the results. I'm just comparing two versions of my own thing because no other algorithm could do that on my machine, right? So this is my last, right? So ArcGIS, this is total. ArcGIS, 6,200 seconds. My algorithm, 6 seconds. Thank you.